Hello, everyone. Thank you very much for joining our webinar on Seismic Symphony, Hidden Structures with Unseen Innovations Developed in East Asia. My name is Maria Liapopoulou. I am the chair of the Second Young Member Subcommittee, and I have the pleasure to welcome Honest Tang, Saad Faizi, and Yao Wang from ARUP to share with us their expertise on seismic design. Before we begin, I would like to ask the audience to please keep your video cameras off and your microphones on mute during the presentations. We will have a Q&A session at the end, and if you have any questions in the meantime, please type them in the chat. Also, please note that the seminar is recorded and will be uploaded on our second YouTube channel. So by dialing into this event, you agree that any information or views you share will be made public. Now, some updates from second. The second fund is open for applications. This scheme offers up to £1,500 of financial support to individuals or teams in the field of engineering dynamics. Some examples of what you can use the second fund for include lab tests or fieldwork, development of new engineering tools, or taking part or organizing events related to engineering dynamics. You need to have a valid second membership to apply, and the deadline for applications is 31st of July. So please visit our website for further details and information on how to apply. 2 weeks ago, we hosted at the Institution of Civil Engineers the 19th Mallet Milne lecture, delivered by Professor Calvi from the School of Advanced Studies in Pavia and chaired by Damian Grant from ARUP. This was an excellent lecture on risk management and rehousing of people after earthquakes. If you have missed the lecture or you want to revisit it, the recording is now available on YouTube through the first link on the slide. And you can also check recordings from previous events as well as our podcast episodes on our YouTube channel on the second link of this slide. For those of you attending the site visit to the Schofield Center at Cambridge this Friday, 13 June, we are meeting at 10:45 outside of Cambridge train station. Please try to arrive there on time for a prompt start of the visit, and we will have a tour of the Schofield Center as well as presentations by Professor Madabushi and other researchers in Cambridge. Now back to our event, I will introduce our speakers. Honest Tag is a senior engineer in ARUP with expertise in geotechnical and seismic engineering. His contributions span from deep basement excavations and foundations, rock face stabilization, site formation projects, and in the field of seismic design, Honest has contributed in the drafting of the Hong Kong First Seismic Code of Practice and in various projects on stability assessments of reservoirs in Hong Kong, as well as offshore wind foundations in Japan, South Korea, and Taiwan. Saad Faizi is a project engineer in ARUP with over 6 years of experience and contributions in the field of geotechnical and seismic engineering. Some of the projects that he has involved include offshore foundation, slope upgrading, excavation and lateral support, deep foundation design, and site investigation and formation. With respect to seismic design, Saad has contributed to design standards for buildings in Hong Kong and the first code of seismic design in Hong Kong, as well as to offshore wind foundation projects. And Yao Wang is an engineer in ARUP with 5 years of experience, specializing in foundation design, site investigation and stabilization, seismic design, as well as finite element analysis and numerical modeling. Yao has been involved in large-scale projects, including the C40 Deep Diving Club project, for which we will learn more during the presentations. And his portfolio includes Shanghai, among many other cities in China. Yao has an MSc in Civil Engineering from Delft University of Technology and has published research in seismic and geotechnical engineering. So without further delay, I will now hand over to Honest to start the presentations.
Okay, thank you, Maria, for the introduction and all the audience for joining this talk. So since this talk, we're going to talk about the seismic design or project that in East Asia. So I would like to share our experience in this region. Actually, our involved the project that cover over the entire world. So and also all the projects quite interesting. Before that, I need to declare that. So I actually am a geotechnical engineer. So the following presentation, I will focus on the geoseismic part. Yeah. So regarding seismic analysis design, actually involve a couple of the structure. So like it involves the foundation design, like this shallow foundation and the power foundation, and also some retaining structure like retaining wall, and some slope work like the slope stability check, as well as the underground structure like the basement, tunneling, those structures that interact with the soil. This sort of the design actually involve in very projects like the building project, bridge project, energy project like those all onshore and offshore wind structures, and also some mega infrastructure as well as dam. Before doing this geoseismic design or analysis, we also need to do some seismic hazard assessment. Like we need to identify the risk of that site that suffer earthquake. And we also need to check some site response analysis, means that we need to see how the site respond when earthquake comes. And one of the risks, that is the liquefaction. We also need to check whether it's a potential to happen liquefaction. Of course, when we've identified that risk, we also need to propose the mitigation measures to reduce the impact to our structures. For the design, actually, we need to follow or meet the requirements that state in the design guidelines. Actually, in EA, some regions have their own standard, like Japan, Indonesia, and Philippines. They have their own design guidelines and own requirement, especially for those to satisfy the regional practice and also the concern. For those regions that without those local design guidelines for seismic design, then most of them they will follow some international design guideline that like ASCE from USA or EuroCode. But in Hong Kong now, actually we do not have the seismic code. As Maria mentioned, that ARUP is working with Hong Kong government to draft the Hong Kong first seismic design guideline. So now the process is still undergoing. Hopefully we can get it done, and then we can have a more comprehensive design for Hong Kong structures and the other engineering design. Before do the seismic design, actually we need to check the seismic hazard. So this is the experiment that we did recently. Like we do the PSHA, that probabilistic seismic hazard assessment for one of the projects in Japan, and also Korea, as well as the Philippines. So this is the example. And through this study, we will try to work out a more regional specific disease background spectrum. Energy, especially for offshore wind, is emerging business or market in past few years. So actually, I'm involved in a couple of them. The cover in Hong Kong and South Korea. Actually, from now, most of them are from Japan because the government push this renewable energy quite hardly. They put a lot of effort to this business or this market. So this is the maybe this is the old map. You can see the dot, the blue dot is showing the offshore winds or the site location. So I believe now along the Japanese shoreline there are already lots of projects there. So what we do for our offshore wind project, so actually we focus on the foundation design. We can simply split into two parts. First thing is we need to do the seismic hazard assessment. As I mentioned earlier, we need to carry out the liquefaction assessment to identify any liquefaction risk. After that, we need to do the site response analysis to check the how the site responds under certain earthquakes. And then we going to the foundation design. We need to do the dynamic soil structure induction, the DSSI. So actually, we have two methods to do it. For those preliminary study, like the concept design stage, we normally use the pseudostatic analysis to check the dynamic force. For detailed design, or the client want to know more accurate or the more optimization design for their structure, then normally we will carry out time history analysis using advanced analytical software like Astana. Here is some example to show you what they look like. And next, another major infrastructure project that is the building bridge projects. So it cover a different region like the Philippines, Brunei, and also Hong Kong, China. So we mainly focus on the foundation, similar with the offshore wind foundation. We also need to do the seismic hazard assessment as well as the DSSI to check how the seismic impact to the structure. Huawei is also the important infrastructure, but it's slightly different. Is that because most of the this kind of metro station are underground, so we need to do the dynamic soil load imposed on the underground structure. So regarding this kind of analysis, Saad will share his experience in more detail. Apart from that, I just mentioned another type of structure like the reservoir building that we also look into. So you can see here is one of the project that we did for Hong Kong reservoir, and also one of the building in Vietnam we are currently working on. So how we do this analysis here is some advanced analysis example. you can see on the left-hand side, we are simulating the multi-span bridge to check how the soil structure interaction. We did this analysis using Astana. On the right-hand side, here is the LNG tank simulation to see how the impact from the earthquake to the structure. So we model entire the LNG tank and input the time machine at the base to check it and see how the force and the design loading induced. Here is the example of the basement structure simulate using I think this is also using Astana to see the impact to the underground to the underground structure. The right hand side we are simulating the high-rise building with the foundation power foundation especially model in the structure in the model, and to see the impact from the earthquake. Here is the example also showing the model to simulate the one of the offshore wind structure. And from this kind of offshore wind structure, we need to simulate a little bit accurate. The reason is you can see this is just single pile to support a very huge turbine and blade. So once the stability or instability happen, like liquefaction, the entire structure will collapse or overturn. That's the very high risk. So to precisely estimate the liquefaction potential, in the model we used an advanced soil model called SandySand to check the pore water buildup and also the liquefaction risk. And the last project I want to share that is not related to seismic, but it related to dynamic analysis. The project is quite interesting. It's happening in Hong Kong airport. The kind of analysis to carry out the impact, the rapid impact compaction assessment, because they try to compact the land to densify it, but they worry about this the vibration induced will affect the adjacent structures, especially those sensitivity structure. So we carry out this impact assessment to identify the vibration rates. Eventually, or luckily, that all the measure vibration within the limit. So the project went through well. So that's the end of my sharing, and I will pass the stage to Saad to share his experience. Saad, please.
Yeah, thank you so much, Honest. Quite insightful, quite interesting. Let me just quickly share my screen. Okay, you can see my screen now?
Yep.
Okay. So hi everyone, my name is Saad Faizi. I'm a geotechnical engineer in Hong Kong. I'm actually sitting just besides Honest. I currently sit in the geotechnics and energy team in ARUP Hong Kong, and I work mainly on offshore wind farms these days, handling both the foundation design and subsea cable installation in East Asia, various wind farms in East Asia. But in addition to those offshore projects, I also work with the Hong Kong geoseismic team on the seismic analysis and design for a diverse range of projects in different parts of East Asia region. So for my sharing in today's webinar, I thought it would be interesting to share one of our studies involving the seismic analysis of underground station using two distinct and well-known numerical approaches, namely the pseudostatic and dynamic time history. And I think Honest touched upon it in one of his slides briefly as well. So let me just quickly take out my laser pointer. Okay, so this is a quick rundown of what we will discuss in this sharing. I'll try to be brief. I'll try to um, be within my time limit. So in case I'm running out of time, I might actually skim through a few of the results, but rest assured, you can find the details in one of our papers, and I'll talk more about it. So let's first begin with a quick introduction and get ourselves up to speed with the seismic analysis and for the underground structures. Typically, this is what you would see, the loads that you would expect acting on an underground structure like this underground box structure. But when we consider the action of an earthquake, um, you can expect that there would be seismic impact, right? And the seismic behavior of underground structures, understandably, are quite different from from your above structure or above ground structures. And that's primarily because of the fact that you can imagine the underground structures are constrained by the ground itself, so they're not allowed to vibrate freely. The other reason could be that the geometry itself is such that you would expect the length to be much longer than the cross section dimension. So there are key distinct differences in terms of how we assess the seismic behavior of an underground structure. For most of these underground structures, the inertia of the surrounding soil is quite large compared to the inertia of the structure itself. And thus, the seismic design of the underground structure focuses mainly on the deformation of the ground and the impact and its interaction with the structure itself. So this is just to give you an idea of different geometries and how, because we know that for tunnels, they could be circular, there are some box shape as well, um, and they have different seismic characteristics. The box shaped structures that you see on the right over here is expected to go through racking deformation under seismic loading, and they are not seen to transmit loads as efficiently as you would imagine a circular lining, which you can see undergoes ovaling. But if we stop for a moment and talk about the impact of seismic or earthquake on underground structure, past records do indicate that the underground facilities have experienced a lower rate of damage. Um, for these structures, but the recent studies and experiences from projects reveal that underground structures can potentially suffer significant damage when we talk about large earthquake events. So undertaking a proper seismic analysis for these structures is quite crucial. And in this, I would present two of the widely popular approaches. So this one is the first one. This is the deformation-based pseudostatic finite element method, which is a simplified approach and is deemed to be a very convenient way that is widely applied in research and design practices. In this pseudostatic method, what basically we're doing is we're making use of the horizontal free field ground deformation you see over here, derived from the site-specific site response analysis, and it is applied to the boundaries of your finite element or your finite difference model, and you then see the forces and the deformation that act or that are induced in the underground structure itself. I'll talk more about its procedure in later slides. The other approach is the dynamic time history analysis, and Honest touched upon it quite a few of his slides. Over here, you could see some snippets from a few of our projects as well. The one on the left is just sort of, it's, I assure you, it's moving. It's just too subtle. But the dynamic time history analysis is regarded to be more sophisticated, yet more complex. And in this advanced nonlinear finite element approach, everything is modeled explicitly, and the simulation is run in the time domain. And you can see over here, one shows the box structure and the other one shows an offshore wind turbine with monopile. And this is done using ARUP's finite element program called LS-DYNA, which is allows explicit dynamic code that runs in the time domain and is able to incorporate both structural and soil nonlinearity. So I wanted to, because I understand that they're both quite well-established approaches, we wanted to understand how they bore in terms of their applicability and what if we compare the two analysis approaches. So I tried doing a sort of a high level comparison of the two methods on various aspects over here. As you can see, the pseudostatic method, and understandably so, offers a very convenient and a simplistic way to evaluate the effects of the seismic ground motion. But now the question is whether the simplistic method is in fact sufficient or is accurate enough or not. And we also do see that there are certain limitations when we talk about the pseudostatic approaches. For instance, when we talk about the inertia of the structure itself. So, in order to fully understand and assess those two methods, what we ended up doing is we wanted to do a side by side comparison of this two approach. And we made use of an actual project case. And this formed the basis of this study. So, yeah, so we took this comparative study using an actual project of an underground station in East Asia. And over here, it's worth acknowledging that this case study I'm presenting is a joint effort by our team of current and former ARUP colleagues. And we presented these study findings in the World Conference on Earthquake Engineering last year. And for further details and specifics of the study and the results, I would encourage you to give this paper a read. Okay, so let's quickly look at the specifics. So I'm going to go over some key design characteristics. First and foremost is the geometry of the structure itself. So what you're looking at over here is an underground station structure, a typical cross-section, which illustrates the configuration of the underground station. The station is approximately 400-meter long and has two track levels. And they're constructed by the top-down method, and it consists of two lines of diaphragm walls. And you can see internally there is a barrette pile wall as well that supports the two primary slab levels. And then there are some internal slabs and walls that you can see, which allows it to have or to make it in line with the railway line. And this consequently results in some unused volume because of these internal walls and slabs. And we had to backfill this with mass concrete to counteract the buoyancy of the structure. So this is the sort of a gist of the geometry itself. With regard to the ground characteristics here, you can see a simplified profile. You can see that it has the different types of soil, and then you see a bedrock, relatively shallow bedrock around 15 to 16 meter below the ground. And you can see the shear wave velocity plot. On the right, you can see the shear modulus degradation curves. Now, these degradation curves define the reduction of the shear modulus as a function of the shear strain. And they're quite important for not only your free field site response analysis, but also for your time history, as we're going to later touch upon. And these degradation curves were adopted for each of these soils based on literature and previous experiences on similar ground conditions. Then if we talk about the design earthquake motion itself, so the project site is actually located in a region of low to moderate seismicity. And the characteristics of the design earthquake were determined based on a site-specific probabilistic site hazard assessment, so PSHA. And here you can see the uniform hazard response spectrum at bedrock for a 1,000-year return period. Now, if we look at the time history records, they were selected from database of real ground motion with magnitude and distance combinations that contributed most significantly to the hazard at the site itself. We did some spectral matching to perform, to modify the selected time histories such that they match the uniform hazard response spectrum of the site itself. And you can see those spectrally match time histories over here on your right. So with these, some of the key inputs for the analyses that we're going to now talk about, now let's look into those two modeling approaches we were talking about. So the first one you see over here is the pseudostatic site analysis, pseudostatic method. And in order for you to start with pseudostatic method, you first need to get your ground profile, the deformation profile. And in order for you to do so, you need to do a site-specific site response analysis. So that was first done to estimate the maximum lateral ground profile under the design earthquake motions. And over here, we use our finite difference software called Oasis Siren, which allows us to analyze the response of a one-dimensional soil column subjected to an earthquake motion at its base. Um, and in the site response analysis, the earthquake motion was modeled as vertically propagating shear waves, while a series of horizontal layers were specified for the soil column, with each layer being modeled as a non-linear material with hysteretic damping, and the soil damping derived as a function of those defined soil modulus degradation curves. So once the ground profile was determined, we moved to the two other steps, which is to carry out the pseudostatic soil interaction analysis by applying the maximum free field displacement profile to each side boundaries of the finite element model, together with imposing a pseudostatic horizontal acceleration to the whole model, such that we can get a free field lateral displacement profile that's uniform across the entire soil mass. And then we also had to compute the strain compatible stiffness values that were based on the degradation curves, so that they correspond well to the shear strain of the free field site response analysis for the pseudostatic approach. Once we've done that, we move to step 3, which is we apply the same free field condition, which is the boundary condition, applied horizontal acceleration and stuff, to the combined model of the soil mass and the tunnel structure. This underground structure here is considered as a wish-in-place structure and is subject to the imposed seismic loads from these deforming soil profiles. So over here, you see some snippets of our Plexus 2D finite element model that was carried out to do the pseudostatic soil interaction analysis on the station box structure. And yeah, let's jump into the other time history analysis. So this is, I think, another model that you may have seen in Honest's slide. So this is a snippet from our Elizina model for time history analysis. And as I stated before, for this method, the simulation is run in the time domain. So that's the key here, and that allows us to accurately understand the seismic response or the interaction of the structure with the under the earthquake motion. Some key pointers with regards to the time history analysis, just for your reference. In terms of the model and the dimensions of the model, we kept those sufficiently large because we want to ensure that the free field condition is close to the edge of the model. And the ground motion time history records were then applied at the model base as a biaxial earthquake excitation in the horizontal and vertical directions. We had non-reflecting boundary conditions defined at the base of the model. The structural elements you see over here were all modeled as elastic elements. And finally, regarding the soil modeling itself, now we had to do the model of soil non-linearity perfectly. So we used the soil degradation curves for each of those soil types, and we made use of the hysteretic soil constitutive model in Elizina that helps us in capturing the hysteresis in each of the soil under the cyclic loading. And over here, you can see that sort of a simulated hysteresis. And it helps us in capturing the hysteresis of the soil under cyclic loading, where the energy dissipation under the cyclic response can be modeled explicitly and automatically as the area enclosed by the shear strain response hysteresis loop. So these were some of the key things or key considerations for the dynamic time history analysis. So in terms of the results and discussion, the study, we wanted to focus on three aspects of the study. One was to study it under the design earthquake itself. We then wanted to see what happens if we have a very severe form of earthquake. So we considered it to be an increased earthquake motion, which is basically 2 times the design earthquake. And then the third one was to study the response with respect to the mass concrete fill that we have, because that was to induce increased inertial loading. So we did those by comparing the additional bending moment that was induced by the ground motion for the slabs in the different walls. I'm just going to skim through those results in the interest of time because I cannot discuss those in detail. But if you are interested, like I said before, I would encourage you to read the paper for detailed results and discussions. So This over here you see are the slabs, the bending moment profiles of the two slabs, the lower and the top slabs. And the additional bending moment induced here, you can see they were quite, for the design earthquake, they were quite comparable and they were found to match reasonably well when we do both pseudostatic and dynamic time history side by side. Um, with some higher values that we saw for the pseudostatic, which is understandable because we expect it to be more conservative than the time history. But in general, we saw that there was good comparison, and the pseudostatic worked really well. We saw similar sort of results with regards to the wall and the bending moment profiles as well, and this led to a good a fair conclusion that for a design earthquake, for low to moderate sort of a design earthquake, the pseudostatic analysis is performing quite well, as compared to compared to the dynamic time history analysis. However, the interesting bit came when we started looking into the increased ground motion, because that's where we could see that the pseudostatic analysis it tend to overestimate the bending moments. And the difference could be what was more sort of evident or noticeable for the top slab here, for instance, under the increased ground motion. And similarly, for higher ground motion cases, we also saw a similar thing for the diaphragm walls and the internal walls as well. So this was an interesting finding. Um, and then lastly, with regards to the concrete fill, this was an interesting bit because we entered the study with with certain sort of a presumption or a hypothesis that the backfill would have would lead to more sort of inertial mass, and therefore the pseudostatic may not perform that well. But what we noticed for the design earthquake is that it did perform reasonably well, and it led to the understanding of how much the inertia of the structure itself would be relevant when we consider both of these two analyses. So as a conclusion, what we ended up concluding in this study was that the deformation-based pseudostatic finite element is considered to be generally appropriate. And for the presence of fill, there was imposed minor additional inertial loadings. But when it comes to the increased ground motion, that's where we saw some quite good discrepancies. So yeah, that was my bit. So I'll pass it over to, maybe I'll stop sharing my screen. Yeah, I'll pass it over to Yao.
Thank you, sir. Let me quickly share my screen. Okay, so can you see my screen? It's okay. Okay.
Yes, yes.
I'll just start. Yeah. Hello, everyone. I'm honored to be invited to this sharing session, and my topic is seismic analysis of deep diving pool. But actually, I hope to make a last-minute adjustment to my presentation material, because actually for seismic part, we exactly use the same two methods in this project, like pseudostatic method and time history method. And Saad has already made a clearly explanation about the principles. So I just skip this part and mainly focus on the case study. First, a quick introduction about myself and the project team. I'm Wang Yao, a geotechnical engineer from ARUP Shanghai office, and I'm one of the project participants who will walk you through this case study. We also have Wang Mingming, our project engineer, and Liu Shuyi, our structural engineer, joining us online. So we are discussing a deep underground diving pool project in Hangzhou, China. ARUP was responsible for the structural and geotechnical design, including the preliminary structural design and the excavation support system. The pool is quite deep, reaching 42 meters underground. Its shape changes with depths. The upper sections are various rectangular shapes, of different sizes, while the lower part is circular. The site geology is also complex. We have about 25 meters of soil sitting on top of a rock layer. So you can see the line of rock surface. The upper part of the pool is within the soil and the lower part is in the rock. This soil-rock interface is exactly why we needed a carefully seismic analysis, since we want to know how the pool reacts there during the earthquake. And right now the project is almost completed. Here are some construction photos, especially the two on the bottom right. You can see that, which shows the excavation of the foundation pit. Actually, it really looks like a mine shaft, I think. First part, let's talk about the structural design. We made a 3D sketch of the entire pool for better understanding. The pool is supported by board pile, and actually there is a one unique feature I want to point out. It's that at the right corner you can see the circular pool's plan view. While a complete circular section is ideal structurally, but architecture team needed a notch in the inner side of wall for pipe work. This means the inner wall wasn't a perfectly circle. Our solution was to design the pool wall using two non-concentrate circles, which means inner and outside of the wall. This allowed us to largely benefit from the circular shape's advantages while minimizing material use. For designing part, we also used multiple software packages to cross-verify our calculation. First one is it's called YGK, which is a common Chinese structural finite element analysis software. It handled the overall static and seismic design. The software is really simple and efficiency, however, it simplified assumptions, especially for seismic actions means we needed more precise verification. So we use the second software called LS-Dyna. Maybe you all know that, which is a more powerful finite element analysis tool. We use it for detailed analysis on the low-level earthquake actions to get more comprehensive and accurate results. I'll explain this part later. Besides, we use Plexus 3D, a geotechnical finite element analysis software for designing excavation support system. Designing an underground diving pool is more intricate than typical buildings, I would say. For stacked loads, we had to consider both scenarios, like the pool fully filled with water and completely emptied. Plus, the pool experiences external earth pressure and water pressure. In extreme cases, we were dealing with like 300 kilopascal water pressure differential between the inside and outside of the pool. So when the pool is fully filled with water, the rectangular sections of sidewalls were the most critical areas, as shown in the highlighted area of the figure. We had to ensure cracks width in the pool walls remained within limits. For the circular section, when full, the notch area was the most critical point, and no cracks were allowed there. So let's moving to seismic analysis. As I said, we use pseudo-static method and time history method, but here we called seismic displacement method. I think it's just one of pseudo-plastic method, but just different names. In one word, this method is a seismic analysis method for underground structures that equals dynamic interaction, which means shear forces and inertial forces between soil layer and structures into stack loads based on the relative displacements between them. So in this method, the input parameters are shear forces, inertial forces, and dynamic water pressure. This figure shows the software. It calculates bending moments and shear force results, and requirements indicate the pool stays elastic during low-level earthquakes. For precaution earthquake and high-level earthquake, the shear sections could not be yield, and overall deformation had to meet specific criteria. Our calculations confirm these requirements were met. However, as I mentioned before, the seismic displacement method is simplified. Its reliability and design process needed further validation. Also, the critical behavior at the soil-rock interface during earthquake required close scrutiny. So we performed a time history analysis during our Steiner to verify our earlier finding. In this model, the concrete was simulated as an electroplastic material and the reinforcement was modeled separately. Both external soil and rock layers were assigned distinct material properties. But for brevity, we focus on results for lower level earthquake actions, so selecting seismic V based on the pool's natural period of vibration. First, we compared static results for both YGK model and the LS Steiner model. Despite the apparent magnitude of error, we think the absolute displacements are relatively close, confirming our pool model's accuracy. Then for seismic results, LS Steiner's calculated peak soil displacement closely matched the seismic displacement method results, validating our external soil validation. And on the low-level earthquake actions, we extract and analyze the stress results for both pool concrete and reinforcement. The peak stresses in both YGK and LS Steiner models were comparable, showing that the seismic displacement method can indeed be used for basic seismic analysis in this diving pool project. However, LS Steiner revealed more prominent stress concentrations in several pool areas, indicating its higher calculation precision compared to the seismic displacement method. So let's go to the conclusion. To summarize, first of all, it's designing underground diving pool is more complex than standard structures, demanding consideration of intricate load conditions and stricter design requirements. For seismic analysis, Chinese seismic displacement method is suitable for basic analysis for this project, providing correct but less precise results. Time history analysis in LS Steiner offers more accurate results, but required building more complex models and providing extensive input parameters. Actually, we basically spent more than half our time in adjusting and our parameters actually. Due to its location in area with low seismic intensity, the pool designed for static conditions can fundamentally meet requirements for earthquake-resistant behavior. I think that's all I have shared with you. Thank you.
Thank you very much, everyone, for the presentations. You provided an excellent overview of the seismic design and geotechnical projects in ARUP, East Asia. And thanks for sharing in detail the deep diving pool project. I think this is a very interesting case. So now I would like to open the floor for questions from the audience. And I can already see 2 questions in the chat. So would Sushant Shetty would you like to unmute yourself and ask the question? Or I can read it otherwise from the chat.
Thank you, Maria, and thanks for the presentation on this for Saad and Wang. Yeah, my question was more on like how is the extent of this soil mass participation considered? Does that is it proportionally linked to the structure that is buried underground, or what's the methodology that is involved?
May I clarify? are you asking the soil extent that involved for the free field deformation approach? That means the pseudostatic one.
Yeah, that's right.
Okay. Simply speaking, roughly around 2 times, but it's subject to the case. But we can think about we just need to make sure the ground deformation at 2n can evenly distribute across the whole model. So as long as we can satisfy this requirement, so no matter 1 times or 3 times of the basement depth, that is okay. But because the purpose is to ensure the ground can deform as what we get from the site response analysis. That's the final goal. Maybe Saad, you can supplement if.
Yeah, I agree with you. The for the pseudostatic that we did, that was a key consideration, that when we were doing it for the free field, we had to make sure that it had to be, and I think that's what I mentioned as well, that it had to be uniformly across the entire soil mass, and then is when we introduce the structure itself. So in terms of the contribution, I'm not exactly well versed with what could be the right proportion per se, but I would agree with Honest. Yeah, it's a proportional response. Now, how much that is I'm not fully sure about putting a number to it. Yeah. Does that answer your question, Sushant?
Yeah, yes, it is. Thank you.
And we also have a question by Clive Shen. Would you like to unmute yourself and ask the question?
Yes, I think the presentation talking about the time history analysis. So I was wondering what kind of constitutive models you have used or applied in the DINA program.
Oh, maybe I can answer that one. We use so it's called the MAT hysteretic. Basically, it's a hysteretic soil model that we use because we wanted to capture the hysteresis loop and the non-linear and the cyclic behavior of the soil. And it was doing a fine job. So we went ahead and used the hysteretic model.
Is that the hysteric model developed by ARUP itself? Or is yeah.
I'm not sure if I'm not sure about other softwares. Maybe Yao can answer that better. But for LS-DYNA, at least, it's one of the constitutive models in LSN. But I understand that I think other softwares similar to LS-DYNA would also have a similar such hysteretic model.
Okay, yeah, because there are several different types of historical models in, for example, FLAC or plastics. So yeah, but it's all right. Thank you.
Yeah, no problem.
Maybe also a supplement a bit regarding this soil model. So it actually depends on the purpose of your expert. Like if you just consider the cyclic effect, those historic soil model can be used. Actually, there for this kind of historical soil model, there are number of this kind of model can use. But for if you want to check the pore pressure build up, like going to check the liquefaction, then probably there are some more advanced soil model like the sandy sand model I presented previously. You can use to do this assessment or simulation.
Yeah, the pore water generation part is always very tricky and it's very complex. So yeah, sandy sand's a good one. Yeah.
Yeah, that's I think we use the UBC model for that, but that's another software. Yeah. Okay.
Yeah.
Thank you.
Are there any other questions from the audience? You can unmute yourself and ask the question or type in the chat. If not, I would like to ask a question to Saad regarding his presentation. So you showed that you did spectral matching to some earthquake records to match the uniform hazard spectrum. Yeah. So I'd like to ask what method you used exactly for the matching and which software. And then why did you select the uniform hazard spectrum as the target rather than, for example, a design spectrum of a code?
Good question. For the spectral matching, I'm forgetting what software we used. There was one that was, I think it's from UC Berkeley, was used for the spectral matching part. The name is slipping my mind, and I can't exactly recall what was the software for it. But for the uniform hazard spectrum, Honest, would you mind helping me out with this one?
Yeah, sure. So actually there are a few software can do this spectral matching to match the selected time history to the target spectrum. One software we use is called RSP match.
Yeah.
Yeah, I guess because there are a number of the commercial available software that is it can automatically adjust the wave signal to match the target spectrum. Yeah, what we normally use is called RSP match.
Yeah, I'm asking because there is a lot of discussion, right? Whether you scale the record or then you modify the frequency content. So that's a topic of discussion, I guess, how to try to keep it with the lowest modifications possible. Yeah, okay, thanks a lot. Good. And for the part of the target spectrum, there is again a lot of discussion in the literature whether that would be the uniform hazard spectrum or a design spectrum. So yeah, if you could clarify that as well.
For the uniform spectrum, it's my understanding because this part related to those seismology, those experts. Because my understanding is for this one have an assumption saying that all the earthquake source that we consider they have a even contribution to the site. So of course, it maybe this is just assumption because some area, some seismic source may have a high frequency on the earthquake, but in this model or this assessment, we assuming they have equal frequency or equal weight to the study site.
But it's a good question, Maria, and maybe I think I did not know much about this, but we'll definitely sort of also check with our seismologist. So what Honest said, yeah, makes sense. Yeah.
Perfect. Yeah, thanks a lot. Okay. Are there any other questions from the audience? Okay, I don't see anything else. So thank you once again. Well, we have one more question, so maybe we have just a couple of minutes to answer that one. Would you like to ask the question, Baptiste Maurer? Okay, let me just read that quickly. So how do you define the mesh size of the models? Do you iterate to refine the results? And how are ANSYS results used for detailing? And whether there is an in-house software for the reinforcement and the transit loads integrated. So could you maybe just quickly, one of the speakers answer also this question?
I think is it for Yao?
Actually, Saad, I'm not sure, but for our project, we truly did several iteration about the size of our models, but you see it's about it's just a problem of time. So yeah.
For the meshing part, yeah, it's a bit of a pickle to come up with the right mesh size, and we in ARUP we've done created a script to help us in automating that and coming to the, I would say, the optimal or size for the mesh. So that's what we tend to use. I'm not sure about the ANSYS one. Not familiar with the reinforcement part of things. So maybe it's a structural related question. Is it? ANSYS result used for detailing. I know that I just know that there is a software called AdSec. I'm not sure if it's any relevant here, but I'm not a structural engineer, so I can't comment much on this. Yeah, I think none of us are structural engineers. So, yeah.
Okay, great. Good. So I think that hopefully answers the question, and the time is now over. So we need to close the meeting. Thank you once again for your time and your excellent presentations, and many thanks to Jerry for helping organize this event. And thanks also everyone for attending. Have a good day, everyone.
Thank you so much, everyone.
Thank you.
Bye.